Good morning, everybody. We have been discussing about the input impedance, effect of feedback on input impedance of an amplifier. We have seen that in voltage series feedback, that means when the feedback is series, we found that something is coming, some voltage is coming in series with the input signal, and the input impedance of an amplifier goes up with negative feedback, and it goes up by a factor 1 plus beta A. It goes up by 1 plus beta A times. That means RIF is equal to RI into 1 plus beta A. Now we shall see what is the effect of shunt feedback on the voltage shunt feedback on input impedance. So here to the input signal, input signal source is a current source in this particular case. So only in such cases we tend to give current feedback or shunt feedback. So let the current be Is and the feedback current provided be If. From a feedback circuit, we give a current If. We draw a current If from the source into the feedback network. That's why it is negative feedback. If it drives a current into the amplifier, it would have been positive feedback. Since it draws part of the input current, it is negative feedback, and the current which goes into the amplifier is II. Now in the case of a voltage shunt feedback, so it is the output signal is a voltage which is proportional to the input current. AII is the output current, and this current flows through an output impedance R0 into the load. I am not showing rest of the circuit, but it is understandable. Here we have Ri. So this is the feedback amplifier. This is the amplifier without feedback. Now we can determine the ZIF or RIF by applying an input signal and determining the voltage that appears across the input and dividing this by Is, we get the input impedance. So when Is is applied, so what is the voltage? So that appears across the input terminals. That voltage divided by this current gives you the RIF. And so naturally the Is here is equal to II, so this current, the input current plus the feedback current, and the feedback current is, so let me divide the numerator and denominator by II. So here you have IF by II. Please note that this IF is equal to beta times the output voltage V0. IF is equal to the feedback network. By substituting that over here, I get Vi by Ri for II, first of all, can be the input impedance is the input impedance. If I designate it in terms of the complex quantity, it is Zi. Zi is the input impedance of the amplifier. That one is Vi by Ii. Therefore, this is equal to Zi, input impedance of the amplifier without feedback. So divided by 1 plus IF. Now IF can be expressed as beta times V naught, beta times V naught. So beta times V naught by Ii. Please note that V naught to Ii ratio is A, because it is a transimpedance amplifier and output voltage is equal to A times the input current. So V naught is equal to A times Ii. Therefore, this is equal to Zi by 1 plus beta times A itself, and IF is equal to beta times IF is equal to A times II. So II gets cancelled. It is equal to Zi by 1 plus beta A. So it indicates that a shunt feedback reduces the input impedance of an amplifier by 1 plus beta A times. Whereas in the series feedback, the input impedance is increased by 1 plus beta A times. Why is it so? For a particular amount of input current, when an amplifier draws a particular amount of input current, because of negative feedback, actually it draws more current. From the source it draws more current. When you want, say, 1 milliampere here, if it draws 5 milliamperes from the source, that means for 1 milliampere to go through this and 4 milliamperes to go through this, effectively for the same input voltage the current drawn is more. Therefore, the input impedance is so low. So in this particular example, it is 5 times lower than the input impedance of the amplifier without feedback. So it shows that by series feedback you can increase the input impedance, and by shunt feedback you can decrease the input impedance by 1 plus beta A times. Therefore it can be manipulated through feedback. The input impedance can be manipulated through feedback. And I repeat, input impedance is very important from matching with the source, or as far as loading of the source is concerned, input impedance is very important. From both power transfer from the input to the amplifier and loading the input points of view, input impedance is very important. Now let us see the effect of feedback on output impedance. Effect of feedback on output impedance. We have two different connections on the output side. So this is the amplifier and this is the load RL. Typically, in shunt feedback, in voltage feedback, we tap the signal like this, the output voltage like this, and we feed it through the feedback network. This is amplifier, this is feedback network. This is shunt feedback, voltage feedback. And for current feedback, we cut the line here and see that the output current flows through the feedback network. So in both the cases, let us see how the output impedance changes. Now look at the output circuit. In the case of shunt feedback, if you examine the output circuit, so you find that there is a voltage source So A times Vi in the case of the output signal is a voltage signal, and there is R naught, the output impedance of the amplifier without feedback. And now this is connected to the load resistance, RL, and we take the signal like this. And on the input side, we apply either series, either we apply the signal in series or in shunt. Now, since we are interested in the output side, let us concentrate on the output side here. And how do you determine the output impedance? So the output impedance is determined by exciting the remove the load resistance and excite the output by a voltage source V, short circuit the input side, and say it is if it is voltage series feedback, for instance, so there would be some voltage Vf, which feedback voltage which appears across the input side. And when you short circuit the input, please note that this feedback voltage appears at the input side, and the input signal Vi is now equal to, Vf is equal to, or rather Vi is equal to, so minus Vf. Although the input is short circuited, replaced by a short circuit, so because of the feedback voltage, some voltage appears across this, and A times this Vi is the output voltage. And when you drive the output by a voltage V, because of the influence of this, the current gets manipulated. So what is the current now that flows into I naught? So naturally, V is equal to the applied voltage V at the output is equal to I naught into R naught or Z naught, if I represent it as a complex quantity as Z naught, I naught Z naught plus AVI. If the voltage gain of the amplifier is A, then A times Vi is the output voltage, and if I apply Kirchhoff's voltage law here, V is equal to this voltage plus this voltage. So V is equal to I naught into Z naught plus A times Vi. Now, to determine Z naught, I have to find out I naught for a given V and divide V by I naught. Therefore, I will get Z naught as, by dividing this equation by I naught, I will get Z naught as ZOF as, so Z naught, let me call it as ZOF because this is ZO, or Z naught, plus AVI by I naught. Now, AVI by I naught, so Vi can be obtained from Vf itself. So Vi is equal to minus Vf, and Vf is beta times V. Therefore, Vi is equal to, therefore this is equal to this Z naught minus A beta times V by I naught. Now, V by I naught is ZOF, and if I bring it this side, so I'll get ZOF as ZO by 1 plus A beta. This is how the output impedance goes down the moment the feedback is voltage feedback. That means if I tap the output by a parallel connection, the feedback voltage that appears at the input is such that when I apply a voltage source V, it draws more current. If there is no feedback, this Vf would have been 0, and when the input is replaced by a short circuit, this is 0, and ZOF is equal to Z0 itself. But by connecting a feedback here, I am seeing that, so there is a voltage which appears in the output on the output side, and this voltage is such that, so this minus this by Z0 is the output current, and that current is large. With negative feedback, that current is large. So because the current is large, the effective output impedance is low. So Z0 by 1 plus A beta is the effective output impedance. Now we shall see the effect of output impedance when the connection is a series, when the current sampling is done in the output for feedback purposes. So let us look at the output. So if the current sampling of the output signal or current feedback, we tap the output current when the output signal is a current signal. Therefore, I am representing the amplifier output circuit as in this form as a current source, and this I0 is A times the input signal Vi if the input is a voltage signal, otherwise it is II, and this is Z0, and here is the load resistance RL, and we tap the output current by cutting the line and allowing the current to pass through the feedback network. Now, when you apply an output voltage, remove this load and apply a driving voltage of V, you expect some current to flow, and let this current be I, because I use the symbol I0 here, and you will find that in this particular case also, if it is current series feedback, let us take the example of a series feedback. The signal is Vf that appears at the input, and if I replace the input source by a short circuit, let me complete the diagram. So the output signal Vf becomes the input signal itself with opposite sign. And now this current is equal to so here Vi is equal to minus Vf, and this current I is equal to, naturally V by Z0 is the current that flows through this output impedance Z0. So V by Z0 minus I0, because this current is coming out. Minus I0 means minus AVI. And Vi is equal to Vf itself. Therefore, this is equal to V by Z naught plus 8 Vf itself. And if the current direction is this, and this is the opposite to this current direction, therefore here Vf is equal to minus I times beta. Now if you substitute here, you can get V by I, that is ZOF, as Z naught into 1 plus A beta. Because you substitute for Vf here, Vf is equal to minus I beta. Therefore, this is equal to minus A beta into I, and bring it this side. So 1 plus A beta into I is equal to V by Z naught. Therefore, V by I is equal to Z naught into 1 plus A beta. So because of this reason, so the output impedance increases by 1 plus A beta times. So a current tapping here increases the output impedance by 1 plus A beta times. So this is the effect of feedback on the input and output resistances. Now the feedback improves the frequency response or reduces the frequency distortion. Reduction of frequency distortion. Let me first define what is frequency distortion. When the input signal is passed through, say when the input signal is divided into different frequency components, that means if you expand the input signal or if you find the spectrum of the input signal, so you find that different frequency components have different amplitudes. If you decompose the input signal into different frequency components have different amplitudes. Now, from an amplifier, what do you expect an amplifier to do? So you expect an amplifier to amplify the signal, and if you find the spectrum of the output signal, so you should find it in this fashion. The width is same in both cases. I mean, there is an expansion here, but please note that width is same. What you expect is a scaling in amplitude. The spectral shape should remain the same. If this component is 50% of this component, so here also this component should be 50% of this component. In certain amplifiers, like your public addressing system, what happens is the low frequencies and the high frequencies are attenuated more than the mid-band frequencies by amplifiers. So that's why we use equalizers, where we try to boost the bass frequencies and boost the treble frequencies both. And therefore, what we want is, we want the amplifier to have a uniform gain for all frequencies. If gain is given as a function of frequency, the gain to be uniform for all frequencies of interest. But unfortunately, some amplifiers act in different ways. Amplifiers do provide different gains for different frequencies. So because of this reason, the output spectrum may be, low frequencies may get attenuated more, amplified to a lesser extent than the high frequencies, and as a result the output spectrum may look like this, and this is no longer 50% of this in that example. So this is known as frequency distortion, that is different frequencies being amplified by getting amplified by different gains. Now this can be reduced, the frequency distortion can be reduced by means of feedback. Say the gain here is 1000 and gain here is 500. Should be, see this spectrum for this signal and for this signal, we want the gain to be constant, say 1000. The gain to be 1000 for this and for this also. Because of distortion by the amplifier, so let us say the gain is equal to 500 here, 500, and let us say beta is equal to 0.01, and now we have provided feedback and beta is 0.01. Now if you provide a feedback of 0.01, how much would be the gain here? Gain for this frequency after feedback, the gain would be, say this is the gain of the feedback amplifier. After feedback, the gain would be how much? A by 1 plus A beta. So that is equal to 1000 by 1 plus 10 into 0.01, 1000 by 11. And what about the gain for this? Gain at this frequency now? Gain is not 1000, it's only 500. But beta is same, because same feedback, frequency independent feedback is provided. So in which case this is 1 plus, so A beta is in this case 5, so and the gain is equal to 500 by 6. Now in the amplifier without feedback, the ratio of these two gains is 2, or the response of this is only half of this. Now after feedback, what is the response at this frequency compared to the response at this frequency? This 1000 by 11, whereas this is 500 by 6, that means 1000 by 12. Is this response half of that? Much less than that. I mean much better than that. So you will find that the gains are to a good extent equalized with feedback. Hence the feedback reduces the frequency or distortion. And for the same reason, the feedback improves the frequency response of an amplifier. If this is the frequency response of an amplifier, say this is the gain, overall gain, and let me call it as A naught. This is gain versus frequency, gain as a function of frequency, because for different frequencies the gain is different. What are responsible for this? The coupling capacitor and the bypass capacitance are responsible for this low gain at low frequencies, because the bypass doesn't completely bypass at low frequencies, and the coupling capacitors offer some series impedance at low frequencies. It's not negligible. And at high frequencies, the junction capacitance is off. The transistor comes into picture and they short circuit the signal. They bypass the signal between the base and emitter. And because of that, the frequency, the gain falls. Now, if this is the gain without feedback, now with feedback, so the gain would be something like this. So this is the gain with feedback. Now say the 3 dB bandwidth of this amplifier is this. That means this is the 3 dB bandwidth of this amplifier, bandwidth without feedback. And now for this amplifier, so the 3 dB bandwidth is, say this. So this is the bandwidth now. bandwidth with feedback is this much. Please note that the lower cutoff frequency decreases and the upper cutoff frequency increases with feedback. So this is achieved at a loss in the gain. Now what is the gain now? So gain now is A naught by 1 plus A naught beta, where A naught is the midband gain. So there is an increase in the bandwidth, and the increase in the bandwidth is of the order of, with negative feedback, bandwidth is increased, bandwidth with feedback is increased by 1 plus A beta times. Bandwidth with feedback is 1 plus A beta times the bandwidth without feedback. If 1 plus A beta is 10 or 11 in this, as given in this example, the bandwidth will increase by 11 times. So these two are related, frequency distortion, how frequency distortion is improved and how bandwidth is improved. Please note that at this frequency, the response was half of this. That means beyond the 3 dB point, this frequency is. Now that frequency has come into the 3 dB point, because the gain ratio is 1000 by 11 and 1000 by 12. So precisely because of this reason, the bandwidth is improved in the case of negative feedback. Similarly, noise also, like distortion, the noise also is reduced by 1 plus A beta times. If the noise voltage is, say, some 1 volt RMS without feedback, and it would be 1 divided by 1 plus A beta volts RMS if it is with feedback. I am not giving the proof here, but this is what happens with negative feedback. Similarly, the stability is also improved. As I mentioned to you earlier, this stability is with respect to the device parameter variations. If we have an amplifier and the amplifier has parameters like the voltage gain, input impedance and output impedance and so on. If, say, this parameter, the voltage gain, varies for some reason due to either temperature variation or by replacing a transistor amplifier by another amplifier. So we can, the amplifier characteristics change, namely the gain changes in this particular example. Now with feedback, so the effect in the changes is very small. So now you know that with feedback the gain is A by 1 plus A beta. Now if you differentiate AF with respect to A, then you will find that, and you normalize it with respect to AF, differentiate it, you will find that, so this is equal to 1 plus A beta times, so dA by A. If there is a change in this A is V, AV, actually AVF. If there is a 50% change, that means dAV by AV is 0.5 in the amplifier. With feedback, its percentage change would be 1 by 1 plus A beta times the percentage change in A. How do you get it? Simply differentiate it with respect to A. So for a delta A, how much of delta AF is cost can be determined in terms of percentage. To determine it in terms of percentage, you normalize it with AF, and so this is what you will get. This can be easily shown by differentiating this and then dividing it with AF. It's a straightforward result. So please note that it is 1 plus 1 by 1 plus AB dot times the change. So that takes place in the amplifier without feedback. So it is considerably reduced and the stability is considerably improved with feedback, with negative feedback. Any questions? Now let us discuss about a practical circuit and apply the principles and determine the effect of feedback. So let us take the example of voltage series feedback circuit. Let us consider a practical circuit and see the effect on the gain. Let us take a simple circuit of a FET amplifier. This is a FET amplifier, this is VDD. So this is RD, external resistance, and this is grounded. And if you neglect that RG which we are using, the input signal can be applied here, Vs. So it can be applied to between the ground and this point. Now let us use a feedback network. Tap the output signal, take a fraction of it and apply it to the input. So let us take this signal and connect it directly over here, this feedback. And let us also include a load resistance R0 or RL. Let's call it as R0 and let's call it as R1 and R2. Please note that we have tapped the output voltage for feedback purposes, and this output voltage V0 plus minus V0 is tapped, and a fraction of that, what fraction of that? R2 by R1 plus R2 times of that is being fed and applied in series with this voltage source Vs, and so that is applied over here. So please note that the output voltage, the feedback voltage is here R2 by R1 plus R2 times V0. Is this feedback voltage adding to this input source, or it is subtracting with the input source? Please note that this is the feedback voltage Vf, and the positive terminal is getting connected to the negative terminal over here. It is added. The output voltage Vf is added to the input signal. Therefore, the Vi, so that is applied over here, is Vi is equal to Vs plus Vf. So it may appear to you that it is positive feedback, but please note that with Vi and the output voltage, so there is a ratio of in the equivalent circuit you have a current source with the Gm times Vi as the Gm times Vi as the output current source, and that one goes through Rd, R1 and R2 and R0, and that current direction is, output current source direction is, so this is the output current, Gm times Vgs or Gm times Vi. Now output voltage V0 is this Gm into Vi into the parallel combination of RD, R1, R2 and R0. So let us call the whole thing as RL. So this is flowing through this RL in the opposite direction. Therefore, output voltage is minus GM RL into VI, where RL is the parallel combination of RD, R1 plus R2 and R0, and parallel combination of R0. If R0 is not there, it doesn't come into picture. Therefore, gain here, the voltage gain is minus GMRL, and the feedback factor is, so this is the feedback factor, beta. Hence, the voltage gain in this case is equal to minus GM RL by 1 plus A beta, 1 minus A beta, because the feedback is adding to the input signal. Therefore, 1 minus A is minus GM RL into beta is R2 by R1 plus R2. Hence, it is equal to minus GM RL by 1 plus GM RL into R2 by R1 plus R2. So here what we did is, from the circuit we identified what is beta. Of course, we identified the way the signal is adding to the input, and we found the gain without feedback. Gain without feedback, only between Vi and when output is RL is connected without feedback, the gain is minus GMRL. So we determined that, and then we applied the feedback amplifier principles, and then we found the amplifier gain with feedback as A by 1 plus A beta, and this is what we got. And please note that this can be analyzed by simply substituting the equivalent circuit of the amplifier here and analyzing the whole circuit, including the feedback, by directly applying Kashyap's voltage laws and current laws. You will get the same expression. So by applying the principles of feedback amplifier, here we are reducing the analysis, and we got the output like this. Is the feedback negative or positive in this particular case? The feedback is negative because there is a 180 degrees phase shift here in the amplifier. For a rising voltage like this, for this kind of cycle here, the voltage cycle here would be like this. The gain itself is negative and beta is positive. Okay, the net voltage that is fed back here is a negative quantity of this type is adding here. Therefore, the feedback is negative.